Hi there. In this video, we're going to start talking about respiration, and we're going to see what happens to all these NADH molecules that we generate in the TCA cycle. So what's going to happen to those, now we're talking again, we're staying in the mitochondrial zone here, and we're going to see that as these protons move on to an acceptor, what we're going to do, what's going to happen is we're going to charge this mitochondrial membrane to really look like a battery. And in fact, it's almost exactly like a battery. You can stick your imaginary electrodes, and not imaginary, there are some molecular electrodes, and you can measure the difference in potential. And that is shown on this cover of this prominent journal in the field that was published in 2016. So take-home message, the NAD molecules, the electrons on NADH are going to move on to some acceptor, and as a result, the membrane will be polarized. So the acceptor in our cells happens to be oxygen, and they will move on. But what we're going to see is as they move on, they polarize the membrane, and then that polarization of the membrane is used, this battery charging is used to make ATP. So we're going to have a machine that actually makes ATP that takes advantage of this polarization of the membrane. So these are a few things we're going to cover in this series of videos. We're going to start on this one with the basic concepts. So the problem, not the problem, but the general thing we're going to see is that the general theme that the electrons on NADH will find an acceptor. So, and the ultimate goal, of course, is to make ATP. So if we go back to our equations for the delta E, we have some features that we expect from this acceptor. So let me switch screens, and we can just really quickly draw on the board. Yes. So the reactions, if we write them as half cells again, is gonna, and I skip all the protons. Okay, maybe I should put the protons here. Hold on. Okay. And we know that the E value for that is minus 300 millivolts. And we want to have an acceptor that's going to have some properties. So the E value for this to happen, we're going to write in a minute. When we couple this, we want to couple them. We're going to couple the oxidation of NADH, so in reverse, with the reduction of A, as written here for the half cell. Okay, so that's the acceptor. Now, for that to be favorable, the delta E, so the whatever gets reduced has to be more positive, has to have a more positive E value than whatever gets oxidized. So here, how more positive, you may say. So to make ATP, you need a delta E of at least 220 millivolts. I was rounding it up to about 250 millivolts plus 250 millivolts, in the previous discussion we had in glycolysis. The bare minimum is this much. So that means that, the E value, the bare minimum for some electron transport to happen here in a meaningful way, so it can be coupled to ATP, this acceptor has to have an E value of no lower than minus 100 millivolts. Why that is, again, if you couple these reactions, we have whatever gets reduced, which is minus 100, minus the minus 320 for the NAD. So that will give you the plus 220, okay? Now, that's a minimum. So the higher this value is, the more ATP conceptually you can get out of this transport, out of the electron transport. So let's go back to where we were with the slides. And all right, so that's the fundamental reaction. That's the acceptor. What kind of an acceptor? As I said, we need to have at least an acceptor with an E value of minus 100 millivolts. And there are many possibilities. For example, fumarate that we have discussed. Fumarate happens in our guts by E. coli cells. Okay, about 0 the E value, so it's definitely more positive than minus 100. So you can get the electron transport there happening, and you get some delta E that's enough to get you some ATP. But again, the more positive you get, the better it is. The more efficient, no, the greater the differential. So the more ATP, at least in theory, you can get out of it. You get to nitrates, and we're going to see the nitrate reduction, later in the class. It's done by a lot of bacteria, very important. And already there were about, a differential of about 700 to 800 millivolts. So that's pretty good. But it gets even better with iron reduction. So you get iron 3. If you reduce it to iron 2, you have almost a volt in difference. Geobacter does that. That's how it gets its ATP. But nothing beats oxygen. Okay, this is the whole idea. How once oxygen became abundant on Earth by biological processes such as photosynthesis, it's an excellent acceptor. Okay, look at the differential from minus 320 to plus 82. That's 1.1 something volts. So it's huge. So the difference, it's an excellent, oxygen is an excellent acceptor, and NAD can dump them all onto oxygen, and in theory you can get a lot of ATP out of it. So that explains why aerobic respiration, if oxygen is there, aerobic respiration becomes a choice, the obvious choice, the only choice. All these things happen in anaerobic conditions for them. Well, most of these things, like E. coli, which can do both aerobic respiration and fumarate respiration. It does the fumarate respiration only in anaerobic conditions in our gut, for example. All right, so we're going to be dealing in our case here with oxygen. That's a delta E value, very favorable. So where is ATP? There is nothing in this reaction that, as we drew it, that shows any ATP. It's all hypothetical. In theory, we can get ATP. How do we get ATP? People were looking for this for decades, right? So it wasn't obvious. People were looking for ATP in the same sense that they were looking for, that they knew it happens in glycolysis, which we discussed with substrate level phosphorylation. You build up some intermediate phospho compounds and you get ATP. But here we have something different. We have a membrane that's closed. Okay, let's say the inner mitochondrial membrane. It's very tight, and the gray box seems to indicate or depicts here the electron transport. So from the gray box is really this reaction, okay, that moves the electrons from NADH to ultimately to oxygen, okay. And as it does so, this movement of electrons is coupled to the pumping of these plus things from the inside, to the outside. So inside the mitochondria, as the electrons are moving, they are coupled to the pumping of protons outside. As a result, you keep pumping and you have an accumulation of these things here, the balls with the plus sign on it. A lot more on the outside than inside. That polarizes the membrane. If the plus sign is a charge, okay, then you have a difference in voltage. So you have two things happening. Not only you have higher concentration of this stuff, but the charge also is different. The charge difference from the outside to the inside. So you polarize the membrane, you have a battery in a sense. So what happens with the electron transport chain? Because it is coupled to the pumping of ions, you charge the battery. Okay. Now, these things want to go back in. They really want to do it for two reasons. Because there are a lot more of them outside, and because the charge also has built up. There is a lot more positive outside than inside. So naturally, for two different forces, chemical and electric forces, they want to go back in. So the task for the cell is to couple this natural tendency, this favorable, thermodynamically favorable movement. They want to go back inside. If you can couple this with some useful work that you want to make, which in this case, of course, is ATP synthesis, then you couple your battery charging with some useful work. And that's great. And this is exactly what you have with a closed circuit. You know, I don't know if you've ever done it, you take a battery with a few little wires and you have a light bulb or some motor running around. That's what you get. But as you know, if you have a short somewhere in the system, then you won't get your useful energy. Just the electrons will keep running around in this fashion here. So what you really have to ensure is that there is no leakage. Okay. So everything works as long as your battery is not leaky. So the membrane compartment allows that. It's a closed membrane compartment. As I said, the inner mitochondrial membrane is super tight, and so it's not leaky. And also, you don't want to fry your battery. Okay, so the material has to withstand this difference in voltage. And biological membranes, as it turns out, they can sustain an electric potential of up to about 0.5 volt, which is not small. It's quite substantial. And why ions? I mean, I keep showing you these things as pluses here, but it doesn't have to be that. It could just be concentration, right? As long as you build a concentration on the outside that's higher than the inside, the stuff will want to go in. But so why have them charged here? Is there any reason for this? Yes, the reason is that you can create two kinds of imbalances. You have two ways to take you outside of the, far from the equilibrium. You have both the chemical imbalance because you keep moving stuff out, but you also have an electric imbalance. Okay? And the electric imbalance is kind of useful because it transmits very rapidly along membrane surfaces. Okay? So it allows you to have both energy and signal transduction happening. And it turns out that univalent ions like protons and sodium are used to couple metabolic energy, the electron transport from NADH as I described, to work, in this case to, let's say, making ATP or moving, a muscle. Calcium, which is a bivalent cation, is mainly used for signal transduction. Same principle, but you use the calcium movement across membranes to signal something. Okay. How do we describe this thermodynamically? Everything I said hopefully makes sense. You have more on one side from the other. Naturally, they want to go back in an equalizing concentration, for example. And we have seen this. There is a free energy change associated with this transport. When you have two different concentrations of one compound across a membrane. And if you have more outside than inside, if you have more inside than outside, then work must be done to move stuff towards their higher concentration. So that's obvious. How much work? You can again calculate it. I mean, if you know the concentrations, these are the constants. And for 1 mole of A, it will cost you about 1.4 kilocalories. So 1 kilocalories per mole. That's a delta G cost. In this case, it will be positive. Delta G will be positive because you have to do work, which is a fancy way of saying that really the more you pump stuff against the gradient, the harder it is to get the next batch pumped out. Okay, so that's the idea. It gets harder and harder and harder progressively as you keep doing this. Now this number is correct if the stuff you pump out if the stuff you're pumping is uncharged. Now you throw in charge on top of everything, which is what we have here with a positive sign. And then you have another thermodynamic component to get into, to factor in. And the delta G for that is given by this equation, which is the electric potential is shown here, delta psi or delta psi, electric potential. That's the Faraday constant, and that's just the charge of the stuff you're moving. That will give you the delta G. Again, moving positive charges into a positively charged compartment gives you a positive delta G. That's the sign here. And work must be done. It's not free. Now, the plasma membrane has a negative potential, electric potential, okay, which means that cations want to go in. There were more plus charged, positively charged things outside than inside. So the positively charged things want to go back into the cell. So the cell constantly has to pump its positively charged ions out of the cytoplasm. Now, as it is the case for all delta Z's, delta Z's are additive and separable for different reactions. Okay, we remember when we were coupling reactions in glycolysis, as long as the net difference was on the negative, then we know that the pathway can happen thermodynamically. Same thing here. You have to see differently. You can treat them separately, not differently. You can treat them separately. The energy associated with moving charges as opposed to moving just stuff, numbers of things. And these are the two equations. They are additive. You put them together to have the overall delta Z for moving A from 1 to 2. And that is called the electrochemical potential. And it has a new name now. You can, delta mu ion here. And you can get this number, of course, because it is a delta Z in kilocalories per mole or kilojoules per mole. To express it in millivolts, so now we see, we go back and forth, we have energy and currents, and to express this in currents, in millivolts, you divide all the terms by the Faraday constant. And to express in millivolts makes more sense. This tells you how charged your battery is. That's really what you want. You care in this case, kind of in the same way that you care when you go check the battery of your car. And now that's the new form of the equation, and you have all these equations on the slides. I mean, on the video, so you can go back later and look them up. This is just to drive home one key point, which will become obvious in a minute. At equilibrium now, you can keep simplifying. That's the electric potential, and it is another form of the Nernst equation. And this is the key point. At equilibrium, the chemical driving force will be equal to the electric driving force. Remember, you may have more stuff, numbers of one thing on one side of a membrane versus the other. If that thing you want to move in is also charged, you have to take into account how many other charged things of the same sign are where you want to move it in, right? So you want to move protons, let's say from the inside to the outside. If you have other positive charged things outside, that will make your life harder. Even if you have a lot of protons on the inside, you have to take into account the charge, overall charge that is happening on the other side of the membrane too. So there is a chemical driving force and there is an electric driving force, and you can treat them separately, but in the end, at equilibrium, they have to balance each other. So where is ATP here? Again, we have seen no ATP. We have the overall sum of the aerobic respiration. We have electrons from NADH moving onto oxygen to become water and reduce oxygen. Well, this is really how they get coupled. I mean, you have the electron transport chain. The electrons move onto oxygen. You don't even see it here. But as long as you can couple this movement of electrons to the movement of protons across, as long as you pump protons across the mitochondrial membrane in this case, from the inside to the outside, now you build the number of H here, the protons, and the charge, okay? So you have both a chemical and an electric imbalance that you create. That you generate this imbalance by, as the electrons are moving onto oxygen, as you respire. Now, this imbalance really wants to be balanced again. We want to find its equilibrium, so these protons want to go back in. As long as you couple this natural tendency of these protons to go back in with useful work, which in this case is a motor that will make you ATP as the protons move in, then you can make ATP. So you couple the favorable movement of protons back inside the membrane to the unfavorable formation of ATP. But because they are desperate to go back in, these protons, you can actually make ATP, right? This novel idea, now it seems I make it sound so simple here, and obvious, but it was not obvious. In fact, the vast majority, almost everyone in the scientific community, when they were trying to understand how respiration leads to ATP formation, they were thinking more along the lines of glycolysis, like the reactions we discussed. You have phospho intermediates, high energy compounds, substrate level phosphorylation, and you make ATP eventually. They were trying to find the same kind of enzymes here on this membrane, right? But Peter Mitchell came up with a battery idea that I described to you, And he got the Nobel Prize in 1978. It took him several years to convince, a decade or more, to convince the rest of the scientific community. And he was right. And it's not just that. As you will see, this is a very general principle to couple something, to charge a battery and make something else happen here, let's say make ATP. It unified many seemingly disparate and different phenomena, varied phenomena in biology. So this is so widespread. Comes down again, charge your battery, and then you couple this chemiosmotic, this power that you have now, the charged battery, to do useful work of all kinds. And most of, obviously, ATP is the key one. So Peter Mitchell got the Nobel Prize. He was a maverick, and I'm a history buff in general, and especially also for science, as you may have guessed. And of the many people who actually got the Nobel Prize, I can think of very few others that deserve it as much as Peter Mitchell. It was quite astonishing, actually. Back to the equations now. We know that in our cells, in our mitochondria, is really protons that are moving. That's the ion that we're dealing with. So we can simplify further. Here we move on specifically for protons, so we can simplify the equation a little better. Z is now 1 plus 1, so we can take it out. And we have a new term here. If we divide everything by the Faraday constant, we have the proton motive force, which again, that's Peter Mitchell's term that he used. It is the movement of protons of power that gives the force to the cell to do stuff like making ATP. And we're dealing with difference in concentration of protons, which of course is pH. Now, to get to pH, we have to go from the natural log to the logs, to base 10 logs. And now that's our equation at this point. And the delta pH is the pH difference, of course, across the membrane. So you can measure this. And you can measure, the difference in the pH, from the inside to the outside, from the outside to the inside of the mitochondria, and you can measure the voltage difference also, and that gives you a precise number on the proton motive force. That's the whole idea. I mean, it's super, it's quantifiable. You can put a number to it, and you know exactly how much power you have to make stuff, ATP, let's say. Just to remind you here that, when the pH is low, the concentration of protons is actually very high. So that's remember that. All right. Some factoids. You can move a few thousand protons across a biological membrane, and you ask what's the potential, what's the electric potential associated with that. You're going to get about 60 millivolts, minus 60 millivolts. So that's not bad. I mean, that's close to what the plasma membrane, let's say, the electric potential is, and all it takes is a few thousand protons, not much. If you have a potential of about 120 millivolts, remember, a biological membrane can go up to minus 500 millivolts, right? So there is a difference enough. We rarely get there, if ever. But the 120 millivolt difference can support a 100-fold concentration gradient. Okay. Again, remember that you have the chemical and electric imbalance, and that's for a univalent ion. If you have a divalent ion, you can get to 10,000 times difference in concentration. Remember, calcium is a divalent ion, so small movement of calcium, it's really a big trigger here. So perhaps explain why calcium is used for signal transduction and not for energy coupling. All right, so this is our schema again. We have our battery charged, and we're going to make ATP. Is there an alternative? Well, you could reduce CO2. And when you reduce CO2, you get methane. Thermodynamically is actually feasible, but it gives you very low. It has a very low ATP yield. Now, if you can't do it, and nobody else can do it, and it's fine, and you don't have access, let's say, to oxygen. So, for example, some bacteria do it. So methanogens, let's say in the gut of some ruminants of animals, let's say cows and things like this, that's exactly how they make their living. But the differential in the delta E now, you go from minus 140 to 500. You get, there is a 350 millivolt difference. It's enough to get you, 1 ATP. It's not 1100, so it's about 300 or so millivolts. 1100 would have been with oxygen. So it's not as efficient. That's that's why the ATP yield is lower, but it's doable, and that's what they have, and that's what they do. And notice again what the point here, what I was telling you earlier, that some disparate phenomena, actually it's the same principle, and that's the chemiosmotic principle that Peter Mitchell came up with. In this case, the electron transport chain is coupled to the movement of sodium. Okay, it's actually when sodium comes back in, so that's how these bacteria charge their battery, not with protons, with sodium. But the principle is the same, different flavors, but it's really the same fundamental principle. Sodium comes in, you build a concentration difference. Okay, when sodium comes back in, you power ATP formation. You have your ATP motor there that cranks out the ATP. So same thing, same principle. Even though the enzymes are completely different, even the ions that is pumped is different. But that's the brilliance of the chemiosmotic idea that Peter Mitchell had, that all these really are different variations of one theme. Okay, charge your batteries and then couple the movement of ions back into the formation of something that you want to make, like ATP. So we'll finish with this slide, and then with this video, and then we'll continue next time with the actual description of the electron transport chain in our cells. So I will stop here.